Imagine an airplane loading 2,000 pounds extra fuel just because prices running at departure are 10 cents cheaper than destination. Certainly, someone calculated that even carrying the additional fuel to destination, the airline would save $30 during the return flight. And that guy was right. Hauling the return fuel, overweighing the takeoff from destination, with the fuel required to come back home might be less expensive than simply paying the 10-cent additional fare out there. No savings is too small once you have a fleet of E-jets and you fly thousands of routes a year. Indeed, if you save only 1% in fuel, you can conserve from approximately 470,000 kilograms, roughly 1 million pounds a year, in a 20-aircraft fleet. It represents 585,000 liters, or 150,000 gallons. Multiply these numbers by the current jet fuel price, and you will see how much cash that is. The purpose of this video is to examine flight operations factors affecting fuel consumption and provide recommendations to improve fuel usage. Airplanes are designed to have as little drag as possible. Nevertheless, the actual airplane produces some drag, and aerodynamic degradations occur along the life of the airplane. Small airframe degradations accumulated and may lead to significant additional fuel consumption over time. Dirt accumulation along the airplane skin increases friction drag and reduces specific range. Aerodynamic deterioration such as missing parts, mismatched doors and windows, leaking seals, outer rigging surfaces, protuberances or dents in regions exposed to rough airflow, such as wings and nose, and improperly executed surface repairs, can cause significant performance losses. Flight crews might help in finding drag spots by carefully walking around the airplane for surface distortions, interruptions, skin waviness that could affect drag. Significant power loss may also result from aerodynamic degradation on engines. Check the engines for damaged or dirty fan blades and vanes, or excessive blade tip erosion. The heavier the aircraft, the higher the fuel consumption. Carrying additional and unnecessary weight to destination makes the aircraft heavier and increases fuel burn. Keeping takeoff weight at its lowest, either controlling the operating empty weight, or the payload, or the fuel, or all, will save a lot of fuel. An aircraft generally gets heavier throughout operational life. A natural operation empty weight increase is 0.15 to 0.25% per year, which tends to stabilize after 10 years at about 2%. This variation requires control for flight planning, though weight growth is almost inevitable. Avoid excess weight by looking for dust, garbage, or water inside the aircraft. Reduce the pantry weight by distributing catering along the route instead of loading all the catering for a sequence of flights. Consider different pantries for charter, international, and domestic flights. The less reserve fuel on board, the less fuel consumed during flight. In a typical short-medium scenario, the alternate trip fuel is the most significant factor when meteorology does not interfere. The rule is obvious. The closer the alternate airport, the less fuel is required. The extra fuel required by the captain's discretion certainly constitutes part of the reserve fuel. This fuel results from uncertainties regarding availability or alternate airport and weather conditions. Good coordination with airline dispatchers and proper assessment of weather forecast might increase flight crew confidence and preserve the natural desire for increased reserves. Adding unnecessary fuel, that fuel in excess of the quantity needed to reach the destination prudently complying with the regulations leads to whole trip fuel increase. It is quite important to avoid unnecessary fuel weight. Precisely plan your flight by calculating the exact fuel quantity to be embarked and make sure ground crews are loading the precise amount of fuel prescribed. Airlines will realize substantial fuel saving by carefully planning routes, making routes as short as possible, shortening approach paths, properly calculating the effects of wind and weather patterns. Precise control of payload and accurate knowledge of all the stuff embarked will avoid overloading an aircraft with surplus fuel. The payload used to calculate the flight plan should be as close as possible to the actual payload of the aircraft. This payload, generally the weight of passengers and baggage, are defined by operating rules as standard values that must be complied with. However, other values may be used if they can be statistically demonstrated so as to get the appropriate payload. Using only one engine during taxi can be used to save fuel. At low aircraft weight, it will even prevent excessive use of brakes to control acceleration. Breakaway thrust for engine-out taxi is increased, which will require care regarding FOD ingestion, jet blast, and noise. One-engine taxi procedures should be planned carefully, and the other factors should be considered by operators before incorporating this policy as operational standards. Ramp slope and surface condition, taxi time to active runway, ramp weight, crew workload, engine warm-up and cooling down period, system limitations, etc. Anyway, flight crews should use discernment when using single-engine operations on the ground and make prevail whenever necessary a two-engine operation to assure safety and efficiency. The main benefits by applying reduced thrust are related to increasing engine's on-wing time. Low thrust lowers ITT, which will result in lower deterioration of the ITT margin to redline. However, compared to full thrust takeoff, reduced thrust will burn slightly more fuel. Low thrust will result in lower rates of climb and more time is spent in low altitudes. The higher the flap retraction altitude, the higher the consumption during takeoff. Minimum flap retraction altitudes are defined by regulations and should be accordingly scheduled, yet considering obstacles along the flight path and airline policy. You can save a lot of fuel during the climb phase, as it represents from 20 to 40% of the trip time and perhaps burns 40% more fuel than cruise. The suggested climb schedule is published on Embraer's flight planning tables and is predicted on the use of climb thrust. During climb, mind the margins to stall and VMO/MMO, respectively depicted by the low airspeed awareness tape and the overspeed bar on the PFD. Climb speeds shall be as high as to prevent stall and must also have some margin to withstand bank angle and appropriate to atmospheric turbulences. It is important for pilots to understand these margins and figure out how weight and altitude can reduce them. Climbing using high speed above 10,000 feet will produce additional fuel burn. The higher the speed, the longer the climb distance, the higher the fuel consumption. The effect of increasing altitude is to increase specific range, that is, to decrease fuel consumption. However, for some weights and trip distance, the performance results in lower altitude with the lowest fuel consumption. In other words, there is an optimum altitude. Check the chart. It shows the optimum altitude for various weights. In general, for trip distances greater than 400 nautical miles, the optimum altitude is 37,000 feet. For shorter distances, optimum altitude tables are provided at the Flight Planning section of the Airplane Operations Manual. Operating at optimum altitude represents flying at the maximum range for the speed chosen. All flights shall be shown as close as possible to the optimum altitude, except for ATC constraints. As airplane weight decreases due to fuel burn, optimum altitude increases. Getting lighter, the best choice is to change cruise levels with step climbs. The crew member selecting a new cruise altitude might consider the maneuver capability and the associated turbulence level expected. Remember that upon crossing flight levels, your buffet margin will decrease for a constant weight. Normally, 1.3 G margin is equivalent to light to moderate turbulence. 1.5 G is equivalent to moderate to heavy turbulence. The job here is to define the appropriate margin for the weight and speed to be flown at that altitude. Embraer's AOM publishes the cruise altitude capability tables adjusted for different speed, considering 1.27 G buffet margin and 300 feet per minute residual climb. Cruise is as important as climb to save fuel, as it may become the longest phase throughout the flight. Speed variations may lead to significant fuel burn. The key factor is to change speeds to achieve fuel savings. The answer involves drag. For some flight crews, the higher angle of attack associated with lower speeds must result in higher fuel flow due to the added drag. It is not necessarily true, as it depends upon the speed the airplane is operating. Under normal cruise regime, slowing the airspeed in cruise will actually improve fuel economy. Check how fuel consumption varies with speed. You can find the maximum range cruise Mach. The long-range Mach is also a known figure, which provides significant increase in speed compared to the maximum range Mach, with only 1% loss in specific range. Flying out of the long range, or just 0.2 Mach out of the prescribed speed, may cause a serious increase in fuel consumption. The optimum altitude is normally calculated for zero wind, but wind itself is a factor that may justify operations considerably above or below the optimum altitude. If a stronger wind is present at the optimum altitude, it might be advantageous to fly at a lower and weaker headwind altitude in order to save fuel. Most efficient operations require optimizing altitude for the prevailing wind conditions, and if both factors are combined, the saving is enormous. Keeping the aircraft trimmed at all times minimizes drag and reduces fuel consumption. The autopilot perfectly trims the airplane in pitch, but does not trim for roll and yaw. What the autopilot does is simply apply control displacements to compensate for roll and yaw tendencies, this action going unnoticed by the pilots. The yoke banked to one side is an indication that the aircraft needs directional trimming. To correct it, make sure that the symmetrical thrust is set. Check fuel imbalance and trim the rudder to stop any turning tendency. The airplane is properly trimmed when the control wheel is neutral. Check aircraft trimming during climb and proceed with it during cruise to be sure it is kept okay. Descent plays a less significant role in fuel consumption, as it represents 10% in trip time. Small variations in this part of the flight are not a major concern. However, starting the descent too early, too late, route deviations, interruptions in the descent that required up and down power settings, and changing configuration out of the scheduled profile can cost a lot of extra fuel. The recommended descent should be performed at idle thrust in a clean configuration, normally at MMO/VMO. Reduce the proper turbulence penetration speeds if descending in turbulent air. Using flaps or gear will limit airspeed, thus increasing fuel consumption. Speed reduction should be made using speed brakes rather than flaps. Retract speed brakes before adding thrust. Holding should be accomplished at the highest possible altitude in the clean configuration. Holding with flaps extended can be really expensive. Fewer speed changes and less vectoring during approach are the basics that will prevent a fuel-hungry operation. Sticking to RNP and RNAV approaches is a good means of standardizing procedures and avoid long, unnecessary approach paths and its inherent fuel consumption increase. Whenever possible, shortening the track by fly and VFR approach is the best choice regarding fuel efficiency. Needless to say, the most important factor in an approach is that it should be stabilized and safe. Plan for proper landing flaps consistent with available runway distance and reported braking action. Landing with flaps at 22 degrees will burn 10 kilograms less fuel than with flaps at 45 degrees, but will incur in a landing distance increase. In flight, check the actual landing distance to determine if suitable runway length exists when planning to land with flaps at 22 degrees. Mind the proper techniques to open reverse thrust. It is effective at high speeds and should be deployed after touchdown. If reverse thrust is utilized for safety reasons or company policy, it should be reduced to idle at 60 knots. Taxiing after shutting one engine down can save some fuel, but don't forget to observe the cool down period. Taxiing with engine 2 operating is advantageous regarding the time delay required to connect external ground power. The APU can make the aircraft completely self-sufficient. However, the energy the APU produces is more expensive than the energy produced by similar ground sources. Whenever possible, crews should coordinate the use of GPU and aircraft and spare the APU, thus saving fuel. The APU should be started prior to pushback, just as needed in anticipation for engine start. It should be shut off as soon as it is no longer necessary. Also, there is no need to anticipate APU start before landing. Airport services supplying ground power immediately after blocking and conditioned air for cabin acclimatization will render APU starting useless at all. Actually, the trade-off between engine fuel versus APU usage, accounting for APU fuel plus APU cycle charges, should also be investigated by each airline, aiming at knowing when it is cost-effective to maintain the engines running while waiting for ground service. That's it. We have talked about better flight planning and better maintenance, and no reference has been made to a definite instrument or tool to waste less fuel. But the ultimate fuel saver is the pilot and the technique he uses. Saving a penny in a single journey may appear to be an insignificant contribution for fuel efficiency, but nothing is too small when one is dealing with thousands of flights per year. No matter if it is the case of coping with escalating fuel prices or just improving airline finance to remain profitable. Aircraft should be operated as efficiently as possible, and all unnecessary fuel burn should be minimized.